All right, let's get started. Can everyone hear me all right? Yeah? No? Yep. Sweet. Cool. How was everyone's weekend? Anyone watch anything fun? Any new movies? Any new shows? Nothing? Started Ozarks? What's Ozarks about? I don't think I've heard of it. Maybe I feel like I've heard of it because I can see the logo in my head, but I don't know what it's about, I guess. Um, Cool. They opened a mass grave on Hart Island for deads. Wait, what is Hart Island? Oh, it's a. Oh yeah, yeah. I heard about the one in Bronx. Yeah, yeah, yeah. That was pretty sad. So that was pretty scary. Um, Same drug cartel show, some drug cartel show on Netflix. Yeah, yeah, yeah. So I feel like I can see like the logo for Ozarks on in my head. So I feel like I know what it is, but I haven't seen it yet. Um, Sorry that you've been working, Zach. That sucks. I mean, hopefully you're doing something that you feel is important and that other people feel are important, and it's helping our healthcare workers right now. So hopefully that's rewarding. But yeah, it kind of sucks that you've still been doing that. And yeah, making money is pretty nice. Cool. What did I do this weekend? I watched two movies. So I just got a Hulu subscription. Like I got my free month finally. So the we've been using our free month, and I watched Parasite, which is the best picture from this year. It was interesting because I thought it was like a horror movie given the name is Parasite, and it was like mostly a funny movie. It was like pretty funny. It was kind of a thriller, but like for the most part, I thought it was pretty funny. And then I started watching. Oh, I rewatched A Quiet Place, which is definitely a horror movie, or like at least like I don't know, a thriller at the least. So that was pretty funny, and yeah, like or that was not funny at all. That was very much not a funny movie, but I enjoyed both of them. I've seen A Quiet Place, but I rewatched it, and I was like, this is pretty cool. It's like it was a good movie, and I haven't watched it in like 2 years. The last in that genre that I watched was Bird Box, which just didn't hit me the same way. Like I thought that A Quiet Place was a lot cooler. So that was my weekend. Hopefully y'all had a good weekend as well. But yeah, sounds good. Cool. I'm going to be sharing my screen as usual. Give me a sec. Cool. So today's lecture is on Huffman coding. Has anybody heard of Huffman coding? You can raise your hand if you have. Yeah, I didn't think so. So one person raised their hands, but not too many people have heard of Huffman coding. So good to know. It's going to be new to a lot of us. Today we're going to take a step away from graphs actually, we're going to be taking a step away from graphs for a while now. Probably the next 2 to 3 weeks are going to be away from graphs. And then once we get into our more advanced topics, which are still to be determined, we might jump back into graph algorithms. But for now, we're going to be done with our graph algorithms. A star is going to be the last, or sorry, minimal spanning trees was going to be the last one in our graph part of the syllabus for now. And then we're going to hop back into some more advanced topics later that might be graph related. But for now, we're going to do a small change of scenery. So if you like graphs, bad news. If you don't like graphs, good news. Today we're going to start with Huffman coding, but before I do that, as usual, I have some announcements. Um, cool. So code reviews are due tonight at 11:59 p.m., as you know. If someone didn't give you their link, then you're not going to lose points. Don't worry about that. As long as you send us a screenshot knowing to let us know that they didn't respond to you. So you're not going to be held accountable if someone didn't respond to you. Of course, if you email us and let us know that someone didn't respond to you and you gave them like 6 hours notice or something, that's not going to count. But if you ask them for their link like a day in advance and they didn't give you their link, let us know and you're not going to lose points. We're going to follow up with that person and be like, why aren't you sharing your link? and there's a good chance that they might lose their points if that happens. I'm not trying to make you like rat each other out, but let us know so that you're not losing points. And if you don't want to deal with all of that, just feel free to pick someone from your extra credit list, or even just pick anyone in the classroom, basically, preferably someone who you don't like generally work with. Like if you're looking at code with someone you worked with to like come up with an algorithm together or something, don't pick them to code review, obviously, but you can you can just pick someone else in the class, someone who you didn't work with or whatever, and just review their code. Do you have to submit anything on Canvas for that? Yes. Today, part one of your daily quiz is going to be doing that, and I'll talk about that in a second. The second thing that I wanted to bring up is there's a course review survey. I believe I sent it out this time. Yeah, it's on Slack. And I believe I put up an announcement for it as well. If everyone in a section, just like last time, if everyone in a section does it, everyone gets 10% extra credit on homework 3. I believe the average on homework 3 was around a 69 or 70% across sections. So you can bring that up to about an 80 on the total for the section if every single person, so that's 100% of the section, finishes by 11:59 p.m. Section 2, y'all got all but one person last time, so you had one fewer respondent than the number of people in the class. So that one person, do it again, do it this time, and then y'all will get extra credit. But again, it's either 0 or 100. You either all get extra credit or nobody gets extra credit. And that's because I can't tell who submitted a survey. There's no names, and I don't want to know the names. So all of you have to submit in a section to get the extra credit. Also, the throne of successful completion is with section 4 right now. So if you want to dethrone section 4, then you can beat them this time. This is your chance. So, yep. Fill out that survey. I think that other people can send that survey link on Slack if you don't remember where that is. Did I forget to put the daily quiz in here? 1 second. Oh, okay. I have a daily quiz coming up later. So Yevgeny, to answer your question, I'll show you how to submit the code reviews in about half an hour after we get to our daily quiz. Actually, probably in about an hour. How are we doing on submissions on section 2? I'll check back in on that after lecture. I'm not going to do that right now, but I'll let you know. I think you're a little more than halfway potentially, but I can double check on that. Cool. So the objectives today are going to be to explain how to use a greedy strategy to compress data using Huffman coding. We're also going to perform Huffman coding and Huffman encoding and decoding on example inputs and outputs. And then we're going to use big O notation to give time complexity of Huffman coding. And then lastly, you'll have a chance, we'll probably finish lecture a little early. I want you to take the remaining 20 minutes to implement Huffman coding independently. Please don't just blow that off. It is probably going to come up on your exams. It's going to be very helpful for you to just do it right now and get it out of the way while it's still fresh in your head. So I would just do this after lecture today. You'll probably have time remaining before 11:20 in order for you to actually have time to implement Huffman coding. Cool. So how do computers generally store characters in a string? Again, we're not talking about graphs today. We're actually going to be talking about the innards of how a computer works and how they store different characters in a string. So one of the main ways that characters are stored inside of a computer is ASCII. One of the other ways, there are multiple other ways. For example, oh shoot, I forgot the name of the other popular one. AE256, I believe that's the name of it. That's a different way to use it. But one of the common ways is ASCII. So Unicode, that's what I was thinking of. Unicode we have, and we also have, I believe, AES256, although that might be encryption. I'm not sure. I'm actually going to erase that because I'm not sure if that's encryption or if that is encryption. My bad. Cool. So ASCII and Unicode are two different ways that we store characters in a string. today, as we talk about ASCII, ASCII is one way to represent it, and it basically uses 8 bits. So for those of you who aren't aware, a computer has no idea, for example, what a B is, or an O, or a Z, for example. These don't mean anything to a computer. A computer speaks in a language that consists only of zeros and ones. And what is that language called, where we only have zeros and ones? Does anybody remember? Yeah, binary, or in other words, we call this bit code. So binary is that language, bit code is how we communicate in that language. So a series of zeros and ones that represent different things is referred to as bit code. So bit code is the way that we interface with the computer, but because it's really hard for us to understand bit code and type in only zeros and ones, we have these compilers that break down things that are human friendly. For example, something like this string, dead beef, whatever, that's something that a human might be able to understand and break that down into zeros and ones using a compiler. Compiler basically translates human code into computer code. So ASCII takes in a character, for example, a D, and then it says what 8 bits can represent a D. So I'm totally making this up. Well, actually, I can figure out exactly what this will be. So if we, no, I can't figure this out, but I believe you can use 8 bits to write something like this. Yeah, it's going to be 60, but let's just pretend that this is a representation of D. It could be represented using these 8 bits. 8 bits basically means 8 zeros or ones. So we have 8 total here, and we flip on some bits and we flip off some bits, and then we get this character D here. So this total, these total characters, including spaces, is 36 characters in that sentence, in above sentence. So we use those 36 characters, and each one is represented by 8 bits. So we multiply 8 times 36, and we get 288 bits in order to represent this word here. So that's a lot of bits because that's the maximum number of bits that we might have. If we're talking about it in terms of complexity, it's big O of 8, or L, which is the number of bits to represent one character, times the number of characters. So this is always going to be L times C, where L is the number of where L is the length of the number of bits inside a single character times the number of characters. But the problem here is that this is actually going to be theta. It's going to be exactly bounded by that because it's always going to be 8 bits. How can we do better than that? Anybody have any ideas? Anybody want to raise their hands to share ideas of how we might do better than 8 bits to represent that? No ideas yet? All right, let's keep going then. So one way that we can do it is not fix it to 8 digits. We can say that we don't need all 8 bits. Exactly, Eric. So if we have only a few characters, if not every single character in the English alphabet or whatever alphabet we're using is represented in every single sentence, then we can use fewer than 8 bits. So this is called dynamic length or variable width by, oops, I did not mean to cross that off. This is called variable width or dynamic length of binary coding. I'll also write dynamic length here. And what we do to make it even more efficient, just another way to make it a little bit more efficient, is say the shortest codes are the most frequent characters. So in the above example, what's the most common character? I see a lot of E's, I see a lot of D's. So the D's and the E's might have the fewest bits that we have to represent it, instead of just saying everything is 8 bits. So maybe a D and an E will be like 1 bit each, or maybe 2 bits each, or something like that. So that way we can dramatically reduce the number of characters to represent the entire word or sentence. So we look at this, we say that we have 7 Ds, we have, oh, don't forget the spaces. We have 7 spaces, and we saw 7 Es. So we can represent the spaces, the Cs, and the Ds with much fewer characters than 8, for example. Maybe we'll say that these are represented by 2 characters. But since C and O and T and W only appear once each, maybe we can do something like this is represented by 6 bits or something like that, because it only appears once. So let's just say that it is represented by 6 bits because it doesn't appear that much, and we've already run out of 2-bit combinations, for example. Would we need to store a mapping table? Yeah, we'll go over what the algorithm looks like. So I don't think we're going to have to store a hash map. We're actually going to do this as a tree to encode and decode these. How do you know which characters are shortened? We're actually physically counting how many of these there are, basically. This is a frequency hash map, basically. So we're going to look and say A has 4 occurrences inside of this sentence. So you're physically going to count it before you do a Huffman coding. So you're going to do a frequency, you're going to keep track of the frequencies and use that in order to figure out which characters are most frequent, so which characters should be the shortest. So this is kind of abstract. I've talked about why we want to, or how we do this, why we might want to care about the most frequent ones, frequently occurring characters being shorter length and stuff. But why do we care? Why is this important? And like, why is this going to come into play in real life? Transmitting files over a network. David, do you want to say more about that?
Sure, yeah. So if you have a very large text file and you want to send it to someone, maybe over your phone, but you don't have a good connection, then you might want to first compress it and then send it.
Okay, so compression. Compression was one thing that David mentioned, and large files. And then the third thing was latency, low latency networks, basically. Latency networks. You can hedge processing power to save bandwidth on the network. Exactly. So you can have low latency network connections where you can still send large files on low latency networks. Definitely true. Any other things that we might think about? Take less memory to store. Definitely. Yeah, let's talk about that as well. Space. Space is reduced if we do this. Yeah, definitely. So these are huge reasons. We can compress things to reduce the number of space. We can send large files through low latency networks, basically. We can basically say, is latency not the speed of the network? I thought it was, but I'm not a networks person, so I might be wrong on that. Okay, I'll say low speed network then. Sorry. Cool. So let's say low speed networks. So basically we can use this algorithm, this very, very simple algorithm that we're going to learn in the next 30 minutes to compress huge files and send them over low speed networks with a reduced amount of space. So you guys hit the nail on the head. Why this is important? Because this is going to help us reduce the amount of bandwidth, the amount of data that we're sending over networks to make sure that we can send things efficiently and keep the same level of security that we otherwise would. Maybe we'll still run this through an encrypted network or something, but this isn't going to impact the security of it, but it's going to dramatically reduce the file sizes. Another thing that I wanted to say is this is a very simple compression algorithm that people use all the time to create zip files. So when you see a zip file and you right click on a folder and say compress it, it's literally just doing a Huffman coding. All it's doing is doing this algorithm that we're going to learn, and it's going to actually create a zip file. They even mentioned that creating a zip takes forever. You can quantify by the end of this lecture exactly how long it takes. So that's going to be super fun. At least in terms of complexity, you should be able to say how long a zip file actually takes to make. Of course, there's other stuff that a computer has to do. So like n squared or n cubed isn't going to be the same as like what a computer is actually doing, but you'll be able to tell how fast the actual algorithm is. Um, cool. And as you can see soon, you can save more than 50% of the space with a very simple algorithm that you can probably code up in half an hour. So this is going to help us move much larger sets of data with a simple algorithm that can compress things very easily. It's also used at Facebook to compress nearly all traffic. So pretty much everything that is sent over a wire is compressed using some modified version of Huffman coding, probably something that is a little more efficient, uses some caching and dynamic programming, but basically uses that to compress all network traffic. And the reason behind that is, again, we don't often see certain symbols. Like in the US, you might not see a U with an umlaut being used all the time. So this could have a larger bit code basically associated with it than something as common as an A, an E, a space, etc. So this is something that is super useful in network traffic basically and relaying information across networks. So let's just jump right into it. Let's talk about what Huffman coding is and how we encode and decode using an algorithm. Cool. So I have a sample sentence here, UFO tofu, that we are going to be trying to, decode or encode basically. So our goal is to encode the string below. So we're going to try to represent UFO tofu in terms of by trying to save as much space as we can. So before we get started, how many different characters do we have here? How many total characters? It doesn't have to be unique characters, but how many total characters do we have in this string? And let's say there is no space between the O and the comma. I'm sorry, I kind of indicated that it is. So yeah, 8 different characters. So in an ASCII representation, how much space does that take up? Yeah, comma exists, but the space doesn't. So if we have 8 characters, how many bits of space does it take up? Yeah, 64 bits. I'm fairly certain that this is bits, not bytes. So I think it's 8 bits and not 8 bytes, but I might be wrong on that. I'm actually almost certain that it's bits. So you can represent up to 2 to the 8 different sentences, 2 to the 8 different characters, basically. So this is going to be 64 bits or 8 bytes of data. Yep, so 1 byte equals 8 bits. So 64 bits divided by 8 is going to give us 8 bytes. Do we understand how we got to 64 bits here? We just took how many characters there are. It's not distinct characters, it's total characters. And we take these characters, count them up, so that's 8 total characters. I'm gonna strike out different and say total. So we took 8 total characters, and each one in ASCII is represented by 8 bits. So we multiply the two. 8 times 8 is 64 bits, which is the same as 8 bytes. So that's our baseline. We know that if we come up with an algorithm, we should have at most 64 bits. And we'll see at the end of this how much better Huffman encoding and decoding does to help with that. So the first step in the Huffman algorithm is to count the frequencies of each character. And this is case sensitive. So if you have a capital T and a lowercase t, then they count as different characters. That's very important here. So we counted up the frequencies. I already did this for us. So we see 2 U's, 2 F's, 2 O's, a 1 comma, and 1 T. So again, a comma counts. A comma is a character, and we have to count that. So We've counted up these frequencies. And the next thing that we do is again put each value, like every other algorithm that we've done recently, we put all of these values into a priority queue. Specifically, we put them into a min heap. So again, I've done this for us. We put our comma here with frequency 1. So this time we're representing some node as basically the character as well as its frequency. So keep that in mind. We're basically putting a comma with 1, a T with 1, an O with 2, a U with 2, and F with 2. Does that make sense to us so far? We good to go with how we created that min heap? Any questions on any of that so far? No? Okay, I'll just keep going then. Cool. So now we're going to call extract min twice and add the parent node that combines their frequencies. So I'm going to go ahead and do that actually. And I'm going to do that here. Even though I've already done it, I want to do it again. So if we do extract min twice, what are the two values that we're going to extract out of here? Yeah, so we have the comma and we have the T. So those are going to be the two that we extract out here. So extract min is going to take out the comma and the T. So then we end up reshuffling this a little bit. We've extracted that, we've extracted this. So our new min heap is going to look something like O and 2. So that's going to be our new min heap after we extract comma 1 and T1, basically. Comma 1 and T1. So we've extracted those. And then let's see what it says to do. Add the parent node that combines their frequencies. I actually didn't say what this is. So I'm going to make a note here. Add the parent node to Huffman tree H. So H is going to combine their frequencies, and let's give it some dummy character. Let's say it's *1, and then this combines their frequencies, so it's a total of 2. And so H is going to hold this value of *1, 2, basically. Something that looks like this. And then that is going to have children of those combined things. So the comma 1 and the T1 come off of *1, 2, basically. And then the other thing that we do is take *1, 2 and put it back into our min heap. So this was our min heap, and we put this back into here, which means that we get something that looks like this. We insert that back in and we say O2, U2, F2, and *1, 2. And then we keep repeating 3 and 4 until the min heap has exactly 1 node left. So we have 4 nodes, so we do that again. So if we extract min twice here, what are the two nodes that we're going to extract? O and U or O and U or O and F? Sure. Yep. So let's just start by saying it's O and U, just for the sake of this. And we can say O and U are being extracted. So what's the first thing that we do after we extract O and U, basically? So we're taking out the O and the U, or sorry, we're taking out the O2 and the U2. And then what do we do? Do you remember? We combine the frequencies. So we're going to take these and combine the frequencies. So what's the combined frequency of these two going to be? It's not a trick question. Yep, it's 4. So, and then we name it with some dummy variable *2 now. So we say *2, 4 here. And then we end up pushing this into our Huffman tree as well. So it's going to look something like this, where we have *2, 4 with all of these, and *1, 2 with all of these. Notice that it's not one tree. This is actually now a set of 2 different trees. And they're not combined yet, basically. And we say *2, 4 and *1, 2. For every power of 2, what does that mean, David? Okay. Did you have a question about the algorithm, or are we good to go for now? Curious why we take 2 min? You'll actually see, and we'll be able to tell why very soon. So basically, at this point, we've taken those 2 out, and then we push it back in like we did before. So now we have *1, 2 and *2, 4. And we keep going because the min heap is still not at 1 node yet. So we do that again. We take the F2 and the *1, 2, and we combine those, and we make that *3, 4. And that has children F2 and *1, 2. And then *1, 2, we already saw in our set here. So *1, 2 still has the same comma 1 and T1. Cool. Let's keep going. So we see the same thing that I put up there. We have a set here of these 2 different sets, or these 2 different Huffman trees. And we still have 2 nodes left in our min heap. So we extract min twice, combine the frequencies. So now we're going to see *4, 8. And then that's going to have the 2 children. Or sorry, that's going to be pushed back into the min heap, just like before. So *4, 8. And then we end up pushing *4, 8's children, which are *2, 4 and *3, 4. And then *2, 4 and *3, 4 each have their same children as before, O2 and U2, and then *1, 2 and F2, and comma 1 and T1. Do we have an understanding of how we got to this step right here? Raise your hand if you're confused about that. Okay, sounds good. Let's actually reconstruct this whole thing. Hopefully that helps. Okay. So are you with me so far with why we have these 2 different trees so far? This *2, 4 and *3, 4 here. Does that make sense to us? Raise your hand if that is confusing to us. Okay, so we're still confused about that. So let's step back even more and go through that. Okay, so let's actually, why don't we just go through the entire thing together? I'll start from here. We'll start with the extract min and think about how we got there, basically. So, couple things here. Okay. So, give me 1 second. I'm still setting some stuff up. Okay. So we started with our original tree. I'm actually going to, yeah. Okay. So we started with our original min heap here. And our original min heap had something like, what is the blue tree versus the orange tree? Aha, okay. So the blue tree is going to be our min heap. So this is going to be our min heap. Let me write that down. So this is going to be a min heap. Right now, this is actually also our min heap, labeled with an M. And then we're going to build a Huffman tree, or an H here. So this is going to be an H, and we're going to build a Huffman tree, and that's going to be a set of something that we're going to use to do our Huffman coding, basically. So when we think about Huffman trees, we're basically going to take our original heap, which I'm going to redraw now. Oops. So let's redraw our tree here. So our min heap is going to basically take all of these frequencies that we calculated, and we're going to add them into a min heap. So a min heap is going to have comma and 1 as the root node, a t and a 1 as a child, o and 2 here, and an f and 2, and a u and a 2. Do we understand how we got that min heap? Raise your hand if we're confused about how we got to this min heap here. Okay. Matt is confused. Okay. Cool. So with this, you don't, for some reason, it just showed you raising your hand like 12 times. Cool. So we have these frequencies that we counted. So we counted that there were, oh, okay. So the U was counted twice. So we see 2 U's in our input string. So we see a U here and then a U here, basically. We see an F. We see 2 different F's for the same reason. We see 2 different O's. We see 1 comma, which is this comma right here. And we see a T, which has been counted there. So we get these different frequencies. We're assembling how frequent all of these different characters are, and we store these in a hash map, basically. So we're storing that there are 2 U's, there are 2 F's, 2 O's, 1 comma, and 1 T. We're storing the frequency of each character inside our input string. And then all we're doing is inserting all of these 5 values, the U, F, O, comma, and the T, into a min heap. If we remember with a min heap, the minimum values are above the maximum values. So as far as they can be, they're going to have a 1 here, a 1 here, a 2, 2, and 2. Can the min heap values change based on the order you insert? Absolutely. So this is also to say that we can have T1, comma 1, and then U2, F2, and O2. These are both totally valid min heaps. It doesn't matter what they are as long as they are valid min heaps. So in this case, we might have the T and the comma here. That's totally fine as well. And you'll see that for the purposes of Huffman coding, we might have different encoding schemes, like different trees that come out as a process of this, as a result of this process. But both of them are going to produce valid Huffman codes. And so let's actually just take one. Let's take the one that Arthi had recommended, or let's take the one that we had come up with as our second example. So we have this, and let's actually run through the Huffman algorithm. So this is our min heap. I'm going to rewrite our algorithm here. So we have our min heap, which is this following heap, basically, this following tree here. So again, M here, this M means min heap. So keep that in mind. Okay, so we have our min heap, and we're going to extract 2 from that, basically. So we're going to extract min twice. So we take out the T1, and we take out the U1, or sorry, the comma 1. So we're extracting the 2 min values. So we're extracting min once, and then we're extracting min again. So once we've extracted those, what is our min heap going to look like? Does anybody have an idea of what the min heap might look like once we've extracted min twice? It will just have the U, the F, and the O, exactly. So we're gonna see a U2, F2, and the O2. And then what we're going to, but in no particular order, exactly. Well, it might be different. Like the U is definitely going to be the node, the root node. And the F and the O are going to be the left 2 nodes, but you're right, it doesn't matter what the order is, doesn't really change anything. And then we're going to combine these two, the nodes that we extracted, and have one parent node, star 1, 2. So we're getting the 2 by taking the frequencies here. And then we're just going to add those frequencies together and make a parent node, star 1, 2. And then that is going to have the children that we just extracted, T1 here and comma 1 here. And we're going to add this to our Huffman tree, basically. So this is going to be our value of our Huffman tree. And then we're going to have this as our new min heap, basically. So this is still our value of M, which represents our min heap. And then within the min heap, let me delete all of this. Cool. So now that we've added these into our Huffman tree, we're going to take this new node that we made, this star 1 node, and add it back into our min heap. So we're going to add it into our min heap, and it's going to say star 1, 2 here. Okay, are you with me so far? Does that make sense, or are we still confused about that? Okay. Anybody else? Raise your hand again if you're confused about how we got star 1, 2. We don't take the children? No, you'd never push the children back. You were making an intermediary node, and then we put it into our regular min heap. So that's M. This is our min heap. This is our Huffman tree. So the min heap starts with with all the frequencies, and we're going to make that smaller and smaller, and we're going to make the Huffman tree bigger and bigger, basically. Does that make sense? Yeah, there could be 2 copies of the node and not the same reference. That's fine. Or you can make it the reference. So basically, this could be the reference, for example. But you don't want, or yeah, you probably want 2 different copies. That makes more sense to me. So this is star 1, 2, and this is a copy of star 1, 2 that has its children inside the Huffman tree. So now we're going to run the same exact thing again. So we're going to run extract max twice. What does extract max twice give us? It's going to give us U2 and F2. So Matt, both of these are real trees. I'm not sure what real tree means here, but we're going to use the min heap that we construct in order to make the Huffman tree, which represents our encoding. So we'll go through the algorithm and hopefully that makes sense once we get to that. So we see the U2 and the F2, which is going to be what happens when we call extract min twice. So then what does our min heap look like after that? It's going to have our O2, it's going to have our star 1, 2, and nothing else. So we extract these 2, combine them into a new node, into a new intermediary node. It's going to look something like that. And it's going to have a U2 and an F2. So we're going to see star 2, 4, and U2 and F2. So once we've done this extract max, this goes into our Huffman tree. But one thing to keep in mind is we don't have to combine it with the existing Huffman tree up here. We've made this node and we have a different node here. So star 1, 2 with a T1 and a comma 1. So these just live next to each other for now. So they're not necessarily one tree. They're 2 different trees. We store them in a hash set or something, and we keep them together in some list or a set or something, but they're not related to each other. They don't know about each other yet. So we don't have to know about that yet. But what we do is we add star 2 and 4 into our min heap. So now we keep going and we say, let's get rid of all of this first. So we keep going. So this is our current min heap. And this is our Huffman tree so far, or our set of Huffman trees. So then min heap still has more than one element. So we keep going. We do O2 is our extract min. We extract O2 and we extract star 1, 2. We combine these again. So we do star 3, 4, and it has these two children, O2 and star 1, 2. And then we basically say that we are going to add this into our Huffman tree. But one thing to keep in mind is star 1, 2 already exists in our Huffman tree right here. So what we can say is replace this parent, basically fill in these children here. So we say T1 and comma 1. So what we're doing is basically taking this element here, this star 1, 2 node, and then we're replacing it. We're replacing this childless thing here and filling in its children, basically. So exactly. So we're going to keep taking the min heap, and then we keep doing that until there's only one left. So right now the min heap looks something like star 2, 4. But we have to push in this new element here, which is going to be a star 3, 4, basically. Does that make sense? Did I lose anyone yet? Raise your hand if you're confused about this step where we replaced star 1, 2 with its children. You did lose me. Where did I lose you if you want to vocalize that?
I think you lost me where we made star 1, 2 the top node in the min heap. I was a little lost there. I think. Yeah, that's where.
Star 1, 2, oh, I see, okay. So up here, see how we had O2, star 1, 2, and star 2, 4? We're just calling O2 and star 1, 2, like we're just calling extract min twice. So we're taking out the O and the star 1, 2. Now star 2, 4 is the top of our min heap, basically. Make sense? Okay. And then we're combining these the same way that we did before. We have the O2 and the star 1, 2. We combine them into star 3, 4. We add the 2 plus the 2, which is 4. So star 3, 4 has children O2 and star 1, 2. But we know what star 1, 2 is up here. So star 1, 2 has a T1 and a comma 1 that are already attached to it. So we take those and just add those children in. We add a T1 and we add a comma 1. And then we push this into our Huffman tree. So our Huffman tree is going to have this element, and then it's also going to have the star 2, 4. So we're going to keep this guy the same. So we're going to do star 2, 4, and then it has a U and an F, basically. Sorry. So this is element 2 in our Huffman tree. We still keep the same element 2 in our Huffman tree, star 2, 4, and we just keep that constant. So now, after we do that, we have to push star 3, 4 onto our min heap. Because we just made a new node, we have to push it back into our min heap. So now what we do is we take this again, one last time, and we say this has two elements. It doesn't have one element yet, so we keep doing that. And we say extract min twice. So we're going to take star 2, 4 and star 3, 4. So what does our min heap look like right now? It's empty, yeah. So our min heap is currently null because we've extracted both of the elements in our min heap. So the min heap is null. And then what does our Huffman tree look like? Well, before we do that, let's combine our two nodes. So we have our star 2 and star 3. So let's make a star 4 node. And what is the frequency of star 4 going to be? 8, exactly. So we just take the 4 and the 4. We say this is 8. So now we push this into our min heap. So we push this in and we say our new min heap is star 4, 8. And then we also put this into our Huffman tree. So we say star 4, 8 has a child of star 2, 4. So again, that's this guy. So we combine them to basically look something like this. So we take our star 2 and our star 3, and we say that those are the values here. And then we know what star 2 is, right? So we still have this star 2 way up here. So we can do star 2 and just fill in its children, U and F. So we have a U2 and an F2. And then star 3 has an O and a star 1. So we have O2, star 1, and star 1 has 2. And we have a T down here and a comma here. So again, we're just taking our old Huffman set and we're combining these values. But because we took this value from here, we can just remove it from there. And then this is our new Huffman tree. So we keep doing that until our min heap has one element. Does our min heap have one element exactly right now? Yeah, exactly. So we can just stop right now and say we are done. We have completed building our Huffman tree. And yeah, null counts as one element, but we don't have to worry about the null. Like you can just yeah, I guess null doesn't count as an element basically. When you insert into the min heap, you don't add its children. No, you don't. You add only the root node. So you'd say the star 4, 8, but not the actual children of star 4, 8, for example. So you just add its own value. So this is going to be our Huffman tree that we use for encoding. So step 6, if we go all the way back up here, is until min heap has one node, we have one node, so we're done building our Huffman tree. When the Huffman tree is built, label all left children with 0 and right children with 1. Okay, let's do that. So what I really mean by that is label the edges as 0 and 1. So this is going to look, oops, sorry, this is not the Huffman tree, this is. So we have a 0 here, a 0 here. So left children are going to be labeled as 0s, and then the right children are going to be labeled as 1s. So do we get what we just did here? All we did was go down the left branches and say all the left branches are labeled 0s, all the right branches are labeled 1s. Does that make sense? Anybody, raise your hand if I've lost you this time. Okay, this one seems a little more familiar to people. So we basically say we're taking the 0s and labeling those. And then all we do is now we say that the code for for any leaf node, so we don't care about the stars because they don't appear in our input string, but all of these characters, U, the F, the O, the T, the comma, all of those are leaves, and they all have their own unique, labelings basically. And how we find that is we start at the root and we try to find a U, and we say that a U is a 0, so this 0 and this 0. So U is equal to this 0 and that 0. I'm going to delete this as well. So a U is that 0 and that 0. An F is a 0 here and then a 1 here. An O is a 1 and then a 0. This T is a 1, and a 0. And this comma is a 1, 1, 1. Does that make sense? We're basically going down the tree and saying that a U can be represented by 0, 0. An F can be represented by 0, 1, because we're just following down the branches as we find our root node, as we find our leaf that we care about. So now we look at our string UFO, comma, tofu, and say, what is a U here? How do we represent a U in bit code? 0, 0. So we say in our output string, we're going to have 0, 0. And then what is an F? So 0, 1. Yep. An O is a 1, 0. What about a comma? 1, 1, 1. A T is 1, 1, 0. An O again is 1, 0. F is 0, 1. And a U is 0, 0. So when you traverse through this tree for a letter, you append to a string the path of ones and zeros. And when you hit the current target, you append the whole thing to the big string, which is per se our phrase. Yeah. And you keep doing that until you run out of characters. Exactly. So you take one character at a time, find it in our Huffman tree, and you keep doing that until you're out of characters to parse. And then this is our output string, basically. This is our output string that represents UFO tofu. And let's count the number of characters in this, just as a quick exercise. We have 6, 9, 12, 15, 18 characters. And do you remember how many characters we had in our ASCII representation? So ASCII was, there's no space, no. So we had, in ASCII, we had not 8 characters, we had 18 bits here for 8 characters. In ASCII, we had 8 characters or 64 bits. So yeah, exactly. So this isn't characters, it's actually bits. So we had 8 characters. The same 8 characters in ASCII actually took 64 bits. And in Huffman, it only took 18 bits. So our total compression is like 18 over 64, which is roughly what? Let's see. That's about 2 out of 6. It's about a 1/3 space, which means 66% compression. So we made a string 66% shorter, basically by using this really, really simple algorithm to build our Huffman tree. If space, you just add space to the big string. Yeah, you have to add a new space. You have to rerun the Huffman algorithm and add a space into the tree. But then, yeah, you can add a space somehow and then find the bit code for that. Can you do the same with images? Absolutely. So this can definitely be done on images. You just basically can say, what is this image? Like, what is the pixel representation of this image using RGB? So if you have an RGB value of like 128, 56, 115, you can convert that into a string basically, and then that could represent a character in some sense. So this is also used often for image compression in the same way that Matt just mentioned. So you use this to represent that as a string, and then you can use that in order to do a Huffman coding on it. Great question. Now we've talked about the encoding part. We talked about how we make UFO tofu into this string of ones and zeros. So now, how do we actually take this string and decode it? How do we do a decoding of this string? So I'm going to copy and paste this string that we created together. So we made this string together. How do we decode this into something that we can go back to? How do you use a hash map? What do you mean by that? Well, yeah, like I know that you meant a dictionary, but like how could we use a hash map to do that? We don't know how long each one is. So I think one of the problems that we're going to face is we don't know if 0, 0 is one character or if 0, 0, 0 is one character. So that's going to be a huge problem for us, basically. Like we don't know if the character ends at 0, or it ends at 000. But one thing to keep in mind here is if we look back at our original dictionary, we have values 0, 0, 0, 1, 1, 0, 1, 1, 0, and 1, 1, 1. So this is very, very interesting, basically, where none of these is a prefix for a different one. If 0, 0 is in our map, then you won't see 0, 0, 0 in our map. No, none of these representations is a prefix for anything else. So again, 1, 1, 1 here means that there is no 1, 1 that is being represented. And that is a very, very important property of Huffman coding. There are no prefixes between different elements here. So if 0, 0 is in here, that means that 0 is definitely not in here. So we can basically use that to figure out how to decode this. Alex asked, do we find a character when the null points at when the node points at null? Exactly. So we can basically take in our Huffman tree. So our Huffman tree looked something like this. And then we want to basically take it and parse it into what each character is. So what we're going to do is pass in our Huffman tree. So we're going to parse the encoded binary tree 1 bit at a time. So we take our 0 and we say, traverse down the tree until you get to a leaf. So we take our 0, and a 0 means we go down to the left child. So we go down here, and then we take, are we at a leaf? We're not. So we take the next bit. We take the 1, and we say, cool. We go down to the right child, and then are we at a leaf? Yes, we are. So we take the U. Then for the F, we say, or sorry, not for the F. We take our next bit, so that's a 1, and we say, let's go down to the right. And then we take another 1, so we go down to the other, to the right again. So that's an F. And that's a leaf, so we print out the F, or we add it to our output array. And then the O, we basically go 0, 0, and then we get to this leaf. Then the 1, 0, 0 gets us to a comma, etc., etc. So when the leaf prints whatever the leaf is and continue. Yeah, so this is super easy. We just pass in this Huffman tree to our decoding algorithm. And we can basically say that we just keep parsing this until we get to a leaf. And then you print out the value of the leaf, and then you go to the next character and start from the root again. So we just keep doing that, and we print out UFO tofu. So again, 18 bits of information that we're condensing the information into, and we can still read it the same exact way. We can still use this to represent UFO tofu and go back and forth with that. Does that make sense? Sweet. Now let's hop back into our slides. Today's daily quiz. There's going to be 2 parts to today's daily quiz. So I want you to upload your 3 regular code review URLs, or your 8 if you did your extra credit. I want you to upload them under the Project 2 code review assignment. So what that means is basically you have a commit where you actually commented on the code. Just go to that commit basically and add a URL, like add a link to those URLs so that we can look at your code review comments. If you had issues because you had a code review because a student ghosted you, don't let your TA know. Actually, instead of doing that, put that in Canvas, basically. Just say which student you couldn't reach out to. Couldn't you contact? And if you can, pick someone else in the class. If you can't pick someone else, if you don't have time today or whatever, just let us know. We'll probably just say like sometime in the next month, do another code review or something like that. But hopefully you just do that. What if our reviewee had a ton of commits with different changes and we had to spread over the various commits? that's fine. Just add one of your commits and that should be fine. And we can find your other ones. You don't have to send all of them, just one URL per person at least, please. And then the TAs and I will go over those and start assessing whether those code review comments look good, which, spoilers, they probably all look fine. But if you are mean or unproductive about them, we'll point them out. So yeah, please don't be mean or unproductive. Review your comments and make sure you're being productive about them. And then the second part of the daily quiz for practice is that, oh, sorry, Alan, I did mine on the issue page. Can I just link the issue page? Absolutely, that's totally fine as well. Whatever link you want to send us that shows that you did your work and has the 10 different commit messages per person, basically, or the comments per person. So that's totally fine as well. And then the second part of today's daily quiz is I want you to encode NJIT new work NJ with the commas and the spaces. So there are spaces and commas. And the way that I want you to test that it works is basically encode this, build a Huffman tree using NJIT new work NJ, and then decode it using your Huffman tree to basically test that your output is the right one. So once you do that, you should be able to get back NJIT new work NJ from your Huffman tree if you're decoding it correctly, which means that you know that you did a good job on it. Cool. Is there a separate assignment submission for part one? Yeah, don't worry too much about part one being separate submissions. Like, we're only going to look at the full submission, so don't worry too much about that. Do we write it out like you did? You don't have to write it out. The final tree is totally fine. That's all I'm looking for, basically. And don't forget, you're gonna get 100 if you submit it. The part that you're not going to just get 100 if you submit random stuff is part one. Please submit the actual URLs. And Pablo, if no one has reviewed your code, is anyone looking to review a third person right now? Because if you are, please review Pablo's code. I was really hoping that we wouldn't run into a situation where no one had reviews. So Matt can do it. Cool. Yeah. Awesome. So anyone who wants to review Pablo's can review his for the third person as well. David, if you're still looking for extra credit, you can do that as well. But yeah, code reviews are probably going to be one of the most valuable things you learn in this class. So I strongly recommend that you do it. Sorry, I got disconnected. Let me get back in here. Cool. Any more questions about the daily quiz for today? Let your friends know in other sections. You can talk about it on the Discord for those of you who aren't in this section. Just let them know that this is the daily quiz. This is a super important one because if you can't do this one, then we're going to have to track you down and figure out where your code reviews are, basically. So that would be really, really helpful. Alan, for the second part of the quiz, it's actually in the lesson. It's in like daily quiz lecture 21 or something. There should be a link for that. If there isn't a link, let me know, but I'm pretty sure I made one this weekend. I may have forgotten. Subhashree, can you check on that for me and just make sure that there is a link to submit for that? That would be super helpful. This is due tomorrow at 11:59 p.m. Yes. Pablo? I'll wait on Pablo. When he submits a question, I will answer that. Matt, what's up? Nope. Okay, cool. Both of them had their hands up, but I guess they might still be typing or something. Any other questions that we had? Okay. So let's jump back into Huffman coding. So no worries. What is the efficiency of building the tree, encoding the string, and decoding the string? Let's do this as a partner exercise. So really quickly, what do we think the efficiency of all of these is? What are the bottlenecks? Think out loud to your partner basically, and try to figure out what the bottlenecks are. Take 2 more minutes to think about that out. Think about that with a partner. Please work with someone. All right, let's come back together. Kevin, can you unmute? Are you in a position where you could do that? Mind letting me know? Sweet. What are you thinking about the efficiency of both of these?
The efficiency, I'm thinking it sort of depends on how many different characters we have.
Okay, so let's call the number of characters in our input n. Okay, number of
Right.
characters. And what do we do with all of these characters?
Putting it into a mini heap,
Okay,
or we're counting the characters too.
right. So we have a few different steps. So first we add everything. We count the frequencies. Absolutely right. So how long is it going to take to count the frequency?
Oh, then.
Yeah, exactly. So this is going to be theta of n time. And then how about the space? How much space does that take up?
Oh, then.
Yeah. So
Oh,
theta of n space as well.
yeah.
Okay. Then you talked about building a min heap, basically.
Mm-hmm.
So inside of our min heap, what are we actually doing in terms of min heap operations?
Just extract min and inserting.
Yes. So we have extract min and we have inserts. And how long do each of these take?
Extract min would be O of 1 or constant.
Not quite, because remember what extract min does? Can anybody help Kevin with what extract min does that actually takes up a little extra time? Heapify, yeah. And Kevin, do you remember what heapify, how long heapify takes?
So that could be like the height of the heap.
Exactly,
So like
log n. Yep. So that could take log n, and same with insert, right? Log n for insert as well. So both of these are time. Cool. And then how many times do we actually call extract min and insert?
Insert would be number n.
Yep. So
And
we have
extract would be
inserts.
n as well.
Exactly. So we have O of n inserts and O of n extract mins. So what is our total efficiency then?
Still O of n, right?
Well, it's theta of n for the first step for the frequencies,
Oh, yeah.
plus O of n inserts times log n per insert.
Oh,
So this is going to be O of n plus O of n log n. And what is that equal to?
n log n.
Exactly. Perfect. And then great job, Kevin. You can mute yourself if you want to. I think I've picked on you enough. Why isn't space the number of unique characters? What do you mean? Oh, why isn't space the number of unique characters? It would be. So space could be the number of unique characters, which in the worst case is going to be if everything is unique, right? So that's going to be theta of n, total space. But then we also have to build, so that's going to be for the frequency. And then we also have to build the heap, which is going to be theta of n as well. And then let's see, anything else? I don't think so. Oh, and then the actual tree itself. So the Huffman tree is going to also be theta of n in the worst case. So then we add all of these together and this total space is going to be theta of n as well. Make sense? And then decoding the string, pretty much that should be pretty straightforward, right? Because you already have the tree as the input and so decoding, you take in tree as the input and you take in string as the input. So this is actually going to be super quick because these don't count towards your space because they're inputs. So we basically just go through each of those and we just output what that's going to look like. So the tree, we already know that the tree is balanced. So a total traversal is going to be log n to the root, and we do that n times. So it's going to be n log n to decode the string. And then it's going to be a total space of O of n just for the output string, output space. And then this is going to be time. Sweet. So basically we have n log n to build the tree, encoding the string. I was just counting this as part of it, basically. You iterate over the string and look it up. So O of n for that. And then O of m, the number of bits in the encoding. So basically the size of the output. So again, it could be number of bits. You could refer to it as the number of, yeah, so this is probably better. So to decode, let's talk about the number of bits, not just the number of characters. So then you have a tighter bound, which is O of m there. Yep. And then lastly here, we actually had less time than I expected, but at some point, if you want to go check out these replets, they are basically links to where you can implement Huffman coding yourself. You can encode and decode different strings. So start with the daily quiz, and then if you have extra time during the week, go through these implementations and try to implement them yourself. They are probably going to appear on an exam or homework assignment. This is definitely not homework 4. Homework 4 is going to be covering dynamic programming. So that's going to be a different topic. This is actually never going to appear on a homework, I don't think. So make sure to study this because it's probably going to appear on an exam. Someone asked what the format of the exam is. I'm not sure yet. It's looking likely that we're going to do a take-home exam. I'm almost sure that we're going to do a take-home exam. If it's a yay, that's good. Some people are nervous about take-home exams, but yeah, in one way or another, it's going to be an exam. Keep in mind that the midterm wasn't that easy. This one is probably not going to be that easy either. So make sure you're dedicating a decent amount of time to making sure that you are familiar with all these data structures and algorithms. Cool. Any other questions that we have before I let you proceed with your day? Oh, I have one more announcement. I forgot to specify this. In 2 weeks, April 27th, we're going to have a lecture from, the regularly scheduled lecture is from 11:30 to 12:50. That's going to be another guest lecture. It's going to be a different group of people, and it's going to be a lot of fun. So this is going to be a lot of people who I worked with in the past in my last team. These are some of my favorite people that I've worked with at Facebook. And it's a lot of people who care a lot about diversity, culture, like team building. These are more senior engineers. There's my manager is going to be there, or my old manager is going to be there. One of the PMs who has been at the company for many years and in the industry for a long time is going to be there. So I recommend you attend. I would star that on your calendar. I think it's going to be a super cool lecture. Hopefully you enjoyed the last one. This one is also going to be super fun and interesting. So I recommend that you come if you can. I'll send out more info about their biography or their bios and stuff like that. So you can read up on who they are and what they're doing as well. For the second part of the daily quiz, we have to write code creating a Huffman. No. You do not have to write code. Let me make that clear. You do not have to write code. You have to physically create the Huffman tree. Thank you for asking that question. I was not clear about that. You have to create the Huffman tree manually, the same way we did in lecture, that encodes and decodes a given string. Yep, just sketch it out. Sorry about that. My daily quizzes are usually not that intense where it's going to be like hours of work or anything. When in April is it? It's 2 weeks from today, April 27th, Alex. Yeah, my bad. You do not have to code that. You just have to sketch it out manually. In the code reviews, if the person makes the same mistake in 2 different places, does that count as 2 comments? I mean, I guess, like, you take it as seriously as you want to, I guess, but like, I would try to go for 10 distinct comments. We're not going to penalize you if you can't come up with that, but yeah, 12 is totally fine then. Yeah. I didn't write down the string. Do you mind repeating it for Huffman code? Sure. You can also look at the lecture slides. They should be on there as well. But I believe it's NJIT. Let me just put it here. NJIT Newark, New Jersey, with spaces and commas. Cool. Any more questions? Awesome. Thank you all for coming. This was a good turnout. I think we had over 50 people. So thank you for coming, and I will see you all Wednesday at 11:30 for our next lecture. See ya.